On this lecture, we're going to talk about some of the common sensors available on satellites that are orbiting the Earth's surface. I've classified them under two broad categories. We have the electro-optical imaging sensors and the other microwave sensors. So let's look at each one of these categories of sensors. Now, in the sensors, generally, remote sensing, a sensor is an instrument which records the energy emitted and reflected from the Earth's surface. As we said in previous lecture, there are a wide variety of bands from the electromagnetic spectrum that we cannot see, but using man-made sensors, we can use those sensors to capture the imagery from those bands of frequencies. There are two types, electro-optical imaging sensors and the other microwave sensors. Under electro-optical imaging sensors, they are also called passive sensors. And what do I mean by passive? Passive sensors are sensors that depend upon the reflective energy from the sun, from the earth. Okay, so it is dependent upon the sun emitting its energy on the earth's surface, and that reflected energy is what helps with what is captured by the passive sensors. So electro-optical, they are classified as passive sensors. They do not produce any energy to sense the phenomena. They depend upon the sun. Operate by focusing the energy on a photon-sensitive surface that is sensitive to a designated part of the spectrum. So the new electro-optical imaging sensors, there are a number of detectors that convert those reflected energy from the sun into a set of digital numbers from the different portion of the spectrum. The corresponding electrical signals are then either stored in analog form, and that's long ago. Nowadays, it's now transmitted to your ground receiving center. It uses an optical system similar to a telescope to view the terrain or whatever phenomena it's trying to capture. Instead of a film and image, it's created a light of sensitive detectors that I talked about. These detectors would capture the different portions of the spectrum in different bands, create electrical signals proportional to the brightness of the energy, and then collectively form the image. A single detector can be made to view a strip of terrain by using a set of rotating mirror, and that area it would cover, it's called the field of view area, which is FOV. This is also known as scanning. So yes, a detector is very small, but using mirrors we can make that even a larger area. Usually scanning is done by SWATs perpendicular to flight path. Earlier on in the lecture series I mentioned Landsat covering the Earth's surface at a SWAT of 165 kilometers. Photo detectors, they are also variable. We can have long ago it used to be 20 to 40 detectors. Nowadays we even have thousands of detectors in a single sensor. More detectors we use, the more ability for us to get details, more ability for us to capture different portions of the spectrum. Each value recorded is a simple voltage at a particular instant in time. It's a snapshot, just like a picture. It's not real time. The area detected is instantaneous, and we call that instantaneous FOV, field of view, instantaneous field of view. This is the smallest ground area for which a digital measurement is collected. So an instantaneous field of view can be equated to the size of a pixel for that image. Size of the instantaneous field of view depends upon the height of the satellite, the sensor, and also the resolution of the sensor. Our Landsat SWAT width is 185 kilometers, and here we have it's actually sweeping the terrain as it moves across the Earth's surface, the sensor collects an, a SWOT width of 185 kilometers. So it's very, very coarse, but remember, you're going to have the ability to map the entire Earth's surface within less than a month time. Okay, usually it's 17 to 19 days you can cover the entire surface. Under the electro-optical imaging sensors, there are three subcategories. There are sensors called frame sensors, there are push broom sensors, and also there are mechanical sensors. Let's look at each one of them individually. For your frame sensor, it was originally developed out of the concept of a television, all right, how television works. And of course, the return beam VDCon RBV cameras was used in your satellites to capture aerial images, so visible portion of the spectrum, at a very high altitude for the main intent of capturing overlapping photographs to create 3D models. Imagery was obtained only in the US, so the frame sensor is not being used nowadays. Much more better technology available, but long ago they used to use it. And return beam VDCon cameras, 3 television cameras were used to capture instantaneous photograph, and they use 3 bands, band 1, 2, and 3. Band 1, it ranged to 0.46 micrometer to 0.6 micrometer. Band 2 is the lower red band of the spectrum, which is 0.56 to 0.68 micrometer. Band 3 is the near infrared band of the spectrum, which is 0.66 to 0.83 micrometer. So the frame sensor had at that time actually the ability to capture 3 bands of data from the spectrum. The other type of electro-optical sensor is the push broom sensor. It consists of a linear array of detectors behind a wide angle optical system. So yes, there were an array of detectors collectively as being used to swap the area being orbited across. Each detector is typically sensitive to different parts of the spectrum, so different wave bands, different bands from the spectrum are sensed by the detectors. As the sensor platform moves forward, each detector signal is sampled at regular intervals depending upon the speed. So the sampling of the detectors is done, often. Major problems have been to make the detectors small enough and sufficient uniform in response. Because they're sampling at regular intervals, you have to make sure that they're synchronized, that all of them capture the same imagery at the same time when orbiting the Earth's surface. So the challenge there was to make sure that the detectors of them are well calibrated. This is an example of what the push broom sensor looked like. This is multiple detector elements going through a set of array, a set of lens to focus it properly onto this array of detectors. And this is the instantaneous field of view, your SWOT area. Okay, the satellite is moving in this direction. The principle here, the electronic scanning across the flight path with a large number of discrete photo elements. So the reflective energy from the sun reflects on the Earth's surface, goes through the sensor sandwich of lens, if you want to call it like that, and then it's then sensed by the different detectors, these detectors then converted to a set of digital numbers. In the form of a satellite, usually the satellite would have the optics and the base of the aircraft, and the reflective energy goes into that opening, and at the back end we have the detector array, and as the sensor is moving, it's actually capturing all of the elements within that SWOT width. and we call this the push broom scanning method. The third type of electro-optical sensor is our mechanical sensor. The instantaneous field of view is made to scan rapidly in a series of scan lines. So instead of doing the perpendicular imagery at the base of the sensors, it makes use of rotating mirrors. So you get images that are larger than the SWOT width. Rotating mirrors reflect the radiation received in the instantaneous field of view onto the detectors. The beginning and end of scan line determine the width of the ground SWOT. So it's actually a larger field of view being captured, a SWOT width, sorry. The electronic signals may be stored for later processing, but usually it's sent direct to your ground receiving station. Product long ago was analog image, but nowadays we have digital image, which require further processing. There are two types of mechanical sensors. Now, because of the fact that the mechanical sensors have the ability to capture much more information, wider areas, and of course, different bands of reflected energy from the spectrum, they came up with the first type of mechanical scanner was called multispectral scanner. And the second type, based upon some flaws in the multispectral scanner, they came up with the thematic scanner. Now, the multispectral scanner had several advantages over aerial photograph. It has very high resolution. The waveband span over a wide portion of the spectrum. It ranged from 0.3, so it includes the visible portion of the spectrum, to 14 meters. So that's pretty about the big, a wide portion of the spectrum it has the ability to capture. And also data is displayed in analog form, but also available in digital form. So there are multispectral scanner, it's still being used, and it has a lot of good advantages. The multispectral scanner, this diagram here shows how it works, and instead of airplane there, you might want to say, okay, it's let's put a satellite there. The concept I just wanted to show you here, as the satellite is moving across the Earth's surface, is actually sweeping the area, but the SWOTs, okay, very fast, and this energy, reflected energy, passes through the optics and then sent and focused to the different a huge array of detectors, and that is converted to electrical values, digital numbers, and then stored or sent to your ground receiving station. Multispectral scanner configuration incorporates thermal infrared detectors with digital recording. So they also, because it's a wide range of frequency being captured, it had the ability to get infrared, thermal infrared also. They've developed upon the multispectral scanner to come up with a new, a modified version of it, which is called the thematic scanner. Some books refer to them as thematic mapper. It's a multispectral scanning system similar to the multispectral scanner, except that a thematic sensor records reflected or emitted energy from the visible, reflected infrared, middle infrared, and thermal infrared region of the spectrum. It has high spatial resolution, high spectral capability of capturing different portions of the spectrum, and the resolution is much, much better. It's useful for vegetation, looking at vegetation, the health of vegetation, looking at soil moisture, snow, the snow-capped areas, cloud differentiation, and many, many other types of analyses that is very useful to mankind. Now, the other general type of sensor going back to my first slide where I talked about electro-optical, and then the other type of sensor is the microwave sensor. Well, let's talk about a microwave sensor. It operates in a band of 1 millimeter to 1 meter wavelength. Detection is by an antenna system. Because microwave that is not generated by a source, the microwave that's generated from the sun is very, very small. We need to have an antenna system that is capable of sensing those reflective microwaves. Wavelength sensor can pass through haze, cloud cover, and smoke. So yes, microwave is useful if it can go through these different types of thick cloud cover. There are two types of sensors. We have the microwave radiometer, and then we have radar. Let's look at each one of them. The microwave radiometer, this is a passive sensor, so it actually captures the microwave that is generated from the reflected energy of the sun. It operates in a wavelength from 20 to 100 centimeters. A narrow beam of antenna can be made to scan mechanically or electronically. Because of the low amount of microwave we have, the resolution is poor. Low energy levels of radiation in the wavelength used, and also it's poor because of the high speed of scanning. In order to get some sort of a microwave image, we have to scan it very fast. At the same time, get an antenna system that's able to capture those microwave energy from the sun. And it's because of those variables, the resolution in your microwave image from passive sensor is usually poor. Large area must be sensed at an instant to gather enough energy for satisfactory measurement. And this is used to determine soil moisture in some geological exploration, and there might be one or two other applications that make use of it. So it's not that popular, but it is a data source. Radar is what more popular. It's radio detection and ranging. It operates in wavelength of 1 millimeter to 1 meter. This is an active sensor. So when we see active sensor, it creates or furnishes its own energy. So it's not dependent upon the sun. It can operate during the darkness as well as during the daytime. All weather capable has enabled images to be obtained where weather conditions have prevented aerial photogrammetry. So it is adapted for bad weather conditions. All right, so where we have thick cloud cover, rainy conditions, we can use a radar and still get a very good map of whatever phenomena we want to capture in terms of the wavelength that we are looking at. Once it's within 1 millimeter to 1 meter, yes, we can get a good imagery of it. Radar transmits a particular band of electromagnetic energy towards an object and detects a portion of that energy reflected from the object. So the system sends out its radar energy onto the phenomena, and that reflected energy back to the sensor, and that time delay is used to generate the image. Besides establishing direction to the target, the system also determines the distance by measuring the elapsed time, and putting all these together, the entire image is generated. This is an example diagram of a satellite orbiting the Earth's surface. Radar is sent out. Alright, one pulse of radar pulse is sent to an aircraft. It reaches this house first and then goes back. So the house is recorded first, and then the tree is recorded second. Okay. Each pulse yields a small amount of information, and there are thousands of transmissions per second. These transmissions are then, once it received back by the sensor, radar sensor, it is converted to an image. There are different types. Radar technology is used in a radar called side-looking airborne reader, SLER. You would see quite a few journal articles referring to SLER. It's an aircraft or satellite mounted imaging reader pointing perpendicular to the direction of flight. So it's looking at perpendicular also, hence side looking. Okay. Applications of SLAR are determined by the relative high cost. So it's much more expensive than your passive reader, but it gives you better imagery. It has a rapid rate of data acquisition, and it's sensitive to both surface roughness and moisture content. Another acronym for it is called SAR. Okay, so SLAR, side looking airborne reader, is same to SAR, which is another acronym for it. SLAR, there are certain limitations. Now the challenge here is actually to get a big enough antenna to sense the reflective energy that is sent out by the sensor. That energy has to be captured by an antenna on your satellite. One of the limitations is SLAR imagery is best at close range and can be improved by using a longer antenna. So SLAR was limited to satellites that are closer to the Earth's surface. There's a limit as to the length of the antenna, which can be carried on an aircraft. I mean, if you're gonna have a satellite over the Earth's surface, you don't want to have a huge antenna, and plus other aspects of that satellite need to be orbiting. It's going to take a lot of energy to keep it into orbit. So that's a big limitation in SLAR. However, as good as we are, there were quite a few improvements on the SLAR. One of that being synthetic aperture radar. It makes use of a short antenna that transmits the signals and receives the signals as the aircraft moves along the flight line, and it uses software that has programs that uses mathematics and the antenna size and transforms it in a computer environment into an array of an antenna that is an even larger antenna. The stored signals are analyzed and mathematically so as to give a high resolution image and corresponds to an effective antenna length of hundreds of meters. Okay, so from a small antenna, using computer models and mathematics, they were able to come up with a method of simulating an antenna which is hundreds of meters. In this diagram here, I want to keep it simple in this lecture because it is an introduction to remote sensing. SAR has a small antenna. So this antenna, the sensor sends it out to the phenomena and then reflects it back. And because of the small size of the antenna, there are certain limitations. SAR, what it does is actually it simulates an antenna not visibly on the aircraft or on the satellite, but mathematically in the software. And using the mathematics behind this, a better imagery is generated from it. It's an example of what the synthetic aperture radar look like. You see here, this is your solar panel, this is your satellite, and this is your antenna. All right, it's relatively small compared to the size of the Earth. Same principle as SLAR, but uses image processing to create high resolution images. So small antenna, relatively small to the Earth, but actually this is simulated to hundreds of meters of antenna in the computer model once it's been post-processed. This slide summarizes the general steps of what is done with in synthetic aperture radar. So the image is captured using image side-looking radar. It accumulates the data along the path, illuminated parallel and to the side of the flight direction. So it's only images on the side of the aircraft that is actually captured. Data processing needed to produce the radar images. The motion of the platform is used also in simulating or to synthesize the large antenna or simulate it. The cross track dimension is the range. Near range edge is closest to the nadir point. This is what it consider and in the post processing. The along track dimension is referred to as azimuth, and the resolution is defined from both the range and the azimuth. So by using this synthesis, in order to synthesize the large antenna, they use the range of the data, taking into consideration the nadir point. It also makes use of azimuth in order to generate or synthesize this large antenna. Digital signal processing is used to focus the image and to obtain a higher resolution than is achieved by the conventional radar. So this is a very advanced technology in terms of what is required in post-processing. Usually the ground receiving station would do a lot of these, but as I said earlier on, this is just FYI for your information. And to keep this lecture simple, the details of how this is done is not going to be further presented to you, but for your information, it is one of the common methods or more accurate methods of using microwave in generating an image, and the common method is using the synthetic aperture radar. Alright, this concludes this lecture. As I said in previous lectures, download the PowerPoint presentation, review the notes page, and if you make sure you understand what's going on, and we will continue with the next lecture.